Hello, this is Juan Roberto Honorato at Anastasia, and today with Domingo Ortuzar, we're going to take a look into a quick journey into how we use Ray and how we implemented Ray and Anyscale to speed up our ML processes. So, at Anastasia, we provide a powerful platform with business solutions in mind that enables organizations across different industries to operate AI capacities at scale with a fraction of the resources and effort that it's traditionally needed. Those 2 points of the scale and the resources needed are key, and we'll get back to those in a minute. So today we're going to take a look into a particular problem of ours and how we initially implemented that in pure Python, then what we saw, the issues we faced, and how we came to the need to scale horizontally, and how then we came into Ray and using Ray and Anyscale to solve those, finally seeing some astonishing results that we got. The problem I was referring to is demand prediction. This problem typically reduces the operational expenses of businesses. And this business problem brings lots of challenges and nuances depending on the particular industry you're on. You may want to tackle it in a different way. But at the machine learning level, at least, we can boil it down into a time series forecasting problem. And our approach at Anastasia is to predict using a multimodal ensemble for every item that's needed of prediction. So we can look at it in this diagram. We first start with a dataset from the customer. In this sense, the dataset consists at least of 3 columns. We have a set of items. In this case, the shirt, pants, and shoes are shown. Then for each one of those, we have a series of dates, each one of those having their own values. And we can think of those values, in this case, for example, let's say it's the number of items sold in that particular date. So that data set is fed into a number of models. We've got a pool of models for prediction, and each model will output their own prediction into the future for the values that we want to predict for each one of those items in question. So we have a number of predictions, each one independent on the other. Finally, we have the last step is to ensemble all of those and output a single prediction for each date and item. So we can see the process like this in this diagram. We get the job start signal that comes from our customers, and then there's the time series generation, the data set that we fed into the ML process. This ML process inside, we initially used AWS Batch Managed Service. This service, what it does is to run Docker images, and we would run one instance, EC2 instance, for each model type. So we would end up with the output of all of those into fed and saved into S3. And this diagram, we saw that each EC2 instance was related for a particular type of model. So in our implementation, we had done ourselves the part of parallelizing and running in parallel all of those training and prediction within each instance. And After a number of iterations, we were able to fully the CPU usage that the instances were reporting were at their fullest. We were pretty happy with those results. We considered the code very optimized, but we would then find out that it was not so. Aside from that, we rapidly hit a ceiling. When we tried to vertically scale, we started, when we used the bigger machines that, on a side note, and not so much as a side note, but those machines, the bigger machines, were pretty expensive and meant that the jobs for us were too expensive, the bigger jobs. And also that the big data, we were not able to scale accordingly, and they were taking too long to finish. Lastly, we were seeing some vendor locking. We were just running Docker images, and that's pretty cloud agnostic, but still the way to interact with all of those jobs was not very easy to migrate somewhere else. So why it's hard to solve the issues we were seeing, namely the scaling part and as well the cost. With a particular service that we were using, being AWS Batch, you can do horizontal scaling and in that way process distributedly your dataset. But you still, if you did that, for once, those instances, the ones that you're horizontally scaling, those don't see each other. So it's really hard to maintain a certain state or global state between those and to communicate those machines. To do so, big code changes are required. Also, to make it fault tolerant in order to be able to use spot instances, it's not easy to do. Finally, you can't scale that particular process dynamically when you're running it. You need to ask for the particular resources beforehand and to know them beforehand. So to solve those issues, we looked into a number of alternatives. One of those was this batch mode that was called the multi-node parallel jobs. And especially the fault tolerance part was difficult to implement. So we discarded that. Then the EMR service that's designed for Spark workloads, and even though it can run Python code, it's not designed to do so. So you have a very limited number of libraries available to you. Then we've got the SageMaker suite that if you're running on AWS, that's the most natural choice to look into. But at least when you're running batch jobs, that's underneath the APIs are very similar into batch service. So we discarded that as well. And yeah, finally we came into Ray. We found out about it on the autoscaler. Right from the very beginning, we saw that very small code changes could solve the scaling and the cost issues at the same time. So it looked very attractive for us at first glance. So now I'll hand it off to Domingo to take a look into that particular scenario.
Thank you, Roberto. Hi, everyone. My name is Domingo Ortuzar, and I'm a senior machine learning engineer here at Anastasia. I'm here to talk about a deeper look inside our process with Ray and how it helped us scale better. In the graphic in front, you can see that at first look looks very similar to our AWS batch implementation. The biggest difference is that we are better managing the workload across the different instances. We are also using a head node to properly send the task to the different worker nodes. And we also made some fixes inside our code that allows for every node to work with every single type of model. So how about we take a little closer look inside what's going on in the nodes. So our approach for designing our code was based on queues and actors. We use queues to load up the data from Anastasia's many data sources, both private and open. Then this data is passed down to the consumer actor, who then processes it and creates new prediction. Then these new predictions are then sent to the data transfer actors, who will save it on AWS S3. This allows us to be using all the resources available from different nodes, and we can also experience a great improvement in our both CPU usage and speed. So this allows us to greatly increase our processing speed while decreasing the number of resources used during a job. Now, also another thing that our code allows us to set both manually and automatically the number of actors that are working in the whole entire job. One of the things that we were very surprised to see is that with this type of implementation, we are able to reduce the number of actors used during a process. Now let's look into some of the results we had. So we tested our current reimplementation with the same configuration and the same models that our AWS batch implementation. Also, we are using Anyscale to configure the different clusters. So this implementation reduced the cost by lowering the amount of CPU needed for running a job. Also, the speed of the process, since it increased, it also lowers the time that the AWS instances needed to be up, also lowering the cost. We also got faster results because we're not using one instance per model, but every instance is able to run every single model, making it faster as we are always using all of the resources available. So also one of the surprising results we got is that our per core speed was actually faster than using Python's built-in multiprocessing. So I'll hand it back to Roberto, who can talk to you more about these results.
Okay, thank you, Domingo. Now let's take a closer look into what the details of what Domingo described, what were the results and how we tested them. So we did a test job consisting of 100,000 time series, each with 120 data points per each item. And then we used 384 CPU cores. In the pure Python implementation, the AWS batch, if you recall, the instances were isolated between them and each were processing a single model type. Those were using the on-demand instances, so the price was the full 100% listing price. On the race side, the instances were forming a true cluster setup. We had more instances distributed with fewer CPU cores for each, and we were using spot instances with their discounts associated. We saw a tremendous results. The Ray implementation was 9 times faster and 87% cheaper at the same time. This cost reduction, as Domingo was saying, not only is reflected because of the spot instance cheaper discounts, also we saw that as the instances were able to process more or faster per CPU core, then the whole job in itself was shorter, and thus the price was further decreased. After starting to use the Ray Autoscaler, we came to see more sophisticated issues than before. So, for example, the production use of the Ray Autoscaler requires careful DevOps processes that were not that were managed by AWS service before. Also, the bottlenecks start to be harder to identify when running from your laptop, because you can, the same one of Ray's strengths is that the same code can be run on your laptop and then on the cluster. So if you run on your laptop and you see everything running fine, using all the CPU at hand or the GPUs and etc., it's not easy to identify if you'll have a bottleneck then when you run on the cluster with all that power at hand. And we saw that, so we needed to do some iterations on the code to remedy that. Then also sharing a cluster is not easy to do when you're working on a team, for example. So that brings us to Anyscale. Anyscale makes it extremely easy from the DevOps side, because you have at your disposal Python SDK and an API. Then you've got the versioning and the governance they've taken care of. So you have visibility into who did what and when. Then you can seamlessly manage, share, and run those clusters across multiple teams. That's very helpful for us, especially when you're working on the business. You have multiple people running the same code within the same clusters. And finally, the optimal orchestration of those Ray clusters, it's taken care of by Ray's own creators. So in that sense, if you were to do all of this in-house, you would end up having a whole team dedicated into doing what they're already offering us. So for us, it was very evident that we needed to absorb all of that using Anyscale tool, and instead of using Ray's Autoscaler itself. So to conclude the talk, we can say that implementing these end-to-end AI workloads using Ray, you get like a really simple experience for developers to scale their code, and doing so improves the performance and lowers the cost infrastructure tremendously. And finally, that Anyscale helps you manage and automate those Ray clusters. And with that, thank you for listening. Have a nice day.